So I'm Mark Kurtz. I'm the machine learning lead here at NeuralMagic and specializing in leading the team and creating these sparse models. So let's go ahead and dive in. Hopefully everybody here came to learn a bit more about kind of YOLOv5 and what we did to it to get more performance on it. So the first question is, why did we focus on YOLOv5? Why did we push YOLOv5 out as a result? So this is, this is kind of an example of just comparing. So this is from the Ultralytics website where YOLOv5 is developed. Efficient depth versus the YOLOv5 models. We can see that the performance versus accuracy, right? So performance meaning how many milliseconds per image, and then our accuracy on the y-axis. We can see that it's performing better than efficient depth, and it performs better than YOLOv3 and others. So that's kind of the big thing. Is the next iteration of the popular YOLO research, which was popularized by PJ Reddy at University of Washington. It's a faster and more accurate version than YOLOv3, which was that last version that PJ Reddy pushed out. Additionally, with YOLOv5, it added compound scaling, which was popularized in the efficient net paper. So what do I mean by compound scaling? Well, this is where we're going to scale the depth, width, and the input size of the network. Originally, the YOLO models and object detection models in general were scaled by just changing the input size. So going from 320 by 320, for example, all the way up to 640 by 640. Whenever we add or whenever we expand this input size, we can obviously makes it easier for the model to come in and detect those smaller features that are in the image, but it also helps with detecting larger features as well, just by giving the model more information. What we can also do with that, though, as we expand that input size, is add more layers to it and add more channels to the network. And what that allows is more capacity in the network to be able to process this extra information that we're getting by scaling up the input size. And ultimately, this creates more flexible and accurate models. We can see that there's options for YOLOv5s down here, which we'll go through, and then YOLOv5L, which we'll also go through, right? So we can create a bigger, more accurate model, or we can create a smaller, faster model. This is also the first YOLO implementation to natively support Partswitch. And why is that an important thing? Well, originally the implementations were all through Darknet, and Darknet is a research library, or at least born out of research, and doesn't exactly have the same capabilities or the same support as the bigger machine learning libraries like Partswitch and TensorFlow and Keras. And the big thing about this is that by using PyTorch and Python, it becomes a more flexible code base, because again, we have more support for more features in these. And what that leads to is, one, faster training with FP16 support. So everything, all of our implementations are defaulted to run at FP16, which gets us about 2 times the training speed whenever we're working with these models. Additionally, it also adds in the support for quantization alert training, which PyTorch has built in, and then we put wrappers around. So it enables us to be able to quantize these models in a much more accurate way versus trying to do post-training quantization. Post-training quantization meaning that we're not going to adjust the weights after we quantize, and I'll go through quantization in a little bit. We're not going to adjust the weights. So quantization when we're training allows us to, as we're quantizing models, recover more and make a more accurate model while getting the advantages for speed and size for quantization. And then finally, YOLOv5 is an interesting model in the sense that it's both compute and memory intensive. And what do I mean by that? Well, one is that, especially for YOLOv5L, there's a lot of compute in this network. There are a lot of convolutions and very large convolutions that need to run quickly. And additionally, there are a lot of operators, including, so with the YOLOv5, there was a focus convolution that was added in, which adds a ton of memory transfer. And additionally, the post-processing that happens in YOLOv5 to be able to run an MS and be able to create the bounding boxes also involves a lot of memory transfer. So this can be really bad both for GPUs, but even more so for CPUs. So to kind of dive into, well, how did we fix this, and why is this a good fit for NeuralMagic? Well, one, we specialize in sparsification. Sparsification reduces the compute for this network. So YOLOv5 and YOLOv5L and YOLOv5S, we can come in, significantly reduce the compute by sparsifying. And additionally, The deep sparse engine reduces memory movements. We have proprietary techniques to both leverage that sparsity for compute speedup and also reuse the caches within the CPU architecture to be able to lessen the memory movement and therefore make these significantly more performant. And so I said sparsification quite a few times. So let's just go through a quick overview on that. What do we mean by sparsification? Well, sparsification is a process of removing redundant information from a model. So neural networks are very overparameterized, very large in comparison to more traditional techniques. And that means that there is actually a lot of redundant information in these networks that we can get rid of and therefore leverage for both smaller size as well as faster performance. So the first one is pruning. And pruning, what we're going to do is we're going to take this fully connected network, right? Each channel here, each node is connected to the next node, right? Through these connections, and these are all going to be multiplications and adds as we go through. So we're going to go from a 5-channel to a 4-channel to a 3 to a 2, and all those are going to be connected throughout. What we can come in and do though is get rid of some of these connections by setting them to 0. So we're not going to be transferring any data across those connections by setting them to 0, or any information across those connections by setting them to 0. And what that means is we can actually skip that whenever we're running in the deep sparse engine. So what we end up with is a network that looks more like this, right? So we went from a fully connected network to a not so fully connected network by removing a bunch of these connections that were unimportant to the problem that we were trying to solve. Additionally, we have quantization. So quantization is the process of taking, for example, this weight or activation distribution. So if we're looking at the activations coming into a convolutional layer, we can say that generally they're going to be represented in between 6 and -6. It depends on the model, depends on the implementation and so on, and the data set that we're training on. But usually we'll get a distribution that looks very normal, and additionally has a pretty wide range, but it is banded. And it's banded within this. So what we can do is actually say that at FP32, where we have 32 bits representing floating points, so floating point being these numbers down here, what we can do is actually compress that information into a lesser data representation. The most common one being int8. So what we're going to do is take these FP32 ranges and compress them into a range between 0 and 255, which is what int8 represents. And what we get is this distribution getting compressed into a smaller representation. So we go from 32 bits down to 8 bits and then into an integer representation. So what this allows us to do is reduce memory movement and also get compute speed up from that. Theoretically, for CPUs, 4x for data movement and 4x for the compute speed up. GPUs can do a little bit better on the compute speed up for quantization, but I won't dive into that just now. So now that we've walked through what is sparsification, what is YOLOv5, let's go ahead and take a look at the results. So what we did is we took YOLOv5, applied both pruning and quantization to that model, and then these are the results that we got out of it. So this top one is comparing the deep sparse engine. So I'm going to turn the music off so that I'm not talking over that. The top one is us running deep sparse engine for a sparse int8 YOLOv5, so pruned and quantized. So this is deep sparse running it, and then Onyx runtime below. You can see there's a big difference between Onyx runtime and deep sparse. This is all batch size 1. This is running on a 4-core laptop. So what we can see is at these larger input sizes, we can still even get to almost real time. So very accurate model running real time on an edge deployment, and servers get even bigger advantages for this. What we're looking at here is anywhere from an 8x speed up to a 15x speed up over the top of the next competitor, Onyx runtime, which has a really good implementation for this. Onyx runtime and PyTorch are running about the same speed on CPUs for this implementation. And so to give some better numbers, so faster inference time. So for latency, batch size 1, and running this on a 24-core server, we actually get 3x faster for YOLOv5L and 1.6x for YOLOv5S. This is comparing our sparse implementation to the dense implementation within the neural magic engine within deep sparse. Deep sparse is also optimized to run much faster for the dense models for YOLOv5 as well. So dense will do quite a bit over the top of Onyx runtime as well here. But our sparse results will get you even further. So comparing our sparse to our dense, we're 3x faster and 1.6x faster for YOLOv5S. For throughput, we're 4.3x faster for YOLOv5L and 2.5x faster for YOLOv5S. And then let's also talk about size reduction, because YOLOv5 and these detection models are actually pretty large in terms of deployment sizes. What we can do is actually get down to a 12.6x compression for YOLOv5L, so taking it from about 130 megs down to 11.7 megabytes, right? So a large file download essentially for a mobile app. And additionally, for YOLOv5S, we can actually compress that from a few tens of megabytes all the way down to 3.1 megabytes, which is extremely easy for most downloads to manage on edge deployments or on the server just for storing a lot of these models. Now let's talk over leveraging results, right? So there are kind of a lot of details that we skipped over there in terms of how we created those models. And that's kind of where the magic, the neural magic comes in both how we create these models and how we get that speed up. So the first thing is reducing iteration with recipes. So all of these models that we push up with recipes which encode the hyperparameters for sparsification. So this walks through everything from which layers to prune, to what level, to when to start pruning, to when to start quantizing, and all of that information. All of these recipes are handcrafted by our ML team to maximize recovery at high sparsities. And why is this important? Well, they're tested and fine-tuned across many runs. Actually, creating one of these recipes takes quite a bit of time to nail down these hyperparameters such that we get a highly accurate model that recovers close to the baseline, as well as has maximal sparsity to get performance. So, these models for YOLOv5S, we're getting to 60 to 70% sparse. YOLOv5L is in the 80s, 80% sparse, around 85. So we're sparsifying these models to a high level, and that's what these recipes are encoding. All of our trials that we've done and built in our knowledge into these, so that other users don't have to come in and try and go through that exact same process. You can take these recipes, apply them to your own data set, and be able to leverage all of our knowledge and iteration with your own data sets. And then the other thing to talk over is also sparse transfer learning. So not only with just the recipes, but we're also pushing out these sparse models. So what we do is we create a general sparse architecture on the Cocoa dataset. So this is for the YOLOv5 models. We'll create a general architecture that's sparsified on Cocoa. And what we're going to do is try and transfer those with lottery tickets to other downstream tasks. Lottery tickets being a kind of a very common thing that's popped up quite a bit recently, ever since the lottery ticket hypothesis paper came out. And what the lottery tickets say is that there is a sparse architecture inside of this very dense overparameterized network that we can find that works well for the general task of object detection in this case. What we can do then is push these models up, and they're available on Spark2, and allow you to come in and download those models and then transfer learn the Spark architecture onto your own data set. And this gives all the advantages of the performance that we have with these models, with a much less training time involved there. So, you can realize these results, for example, in a few hours on a single GPU on your own data set, versus applying a recipe, which typically takes a little bit longer to run. And then finally, we have tutorials. So the tutorials allow us to walk through one, how to apply a recipe, and then two, how to use the Spark transfer learning. So we have these tutorials pushed up into SparkML, so we can come through and do that. And then let's see, so we have a question that came in, which was, so can we say that the recipe creation process is similar to hyperparameter optimization? Yeah. So whenever we're creating these recipes, it is mainly just hyperparameter optimization. The problem with pruning in general is that because of the number of hyperparameters involved there, so you have, for example, one sparsity per layer, in addition to a few others for when to start pruning, when to stop pruning, and then additional quantization, which layers are quantized, and things like that. So essentially, we end up with a combinatorial explosion of parameters there. And that's what we're doing internally in the ML team, using our knowledge to be able to create these based off of previous runs that we've done and internal research that we have to be able to create these recipes, which are essentially us going through hyperparameter optimization to be able to get a highly recovered model and highly accurate and very performant. All right. So I guess I'm going to stop here for a second, see if we have any more questions that that are coming in, but otherwise we'll jump into some demos. Let's go ahead and jump into some demos then. So what we're going to walk through is one, how to transfer learn with your private data, and then two, how to benchmark to validate the performance of that model after transfer learning. So I'm going to go ahead and exit out of our slides here. And what we have is a model page for YOLOv5 for getting started. So this is sparsity.neuromagic.com/getting started, getting started/YOLOv5. We also have a short link here, which is neuromagic.com/YOLOv5, which will take you to the same spot. And what this does is ideally gives you some more information on how to apply these techniques that we have to your own data set and be able to leverage these models. Oh, looks like that went to an older version. Not sure why it went to that, but I must have a weird cache on my system. But if you go to that, it should take you to the Sparsity page. So what we have are different elements that we can do. So we can benchmark, example application, example deployment, performance comparisons for different reference, and then for sparse training, sparse transfer learning, and applying recipe. And in addition, you can see the models that we created here, YOLOv5L and YOLOv5S, including their accuracies. Speeds will be pushed up shortly, and then additionally their compressed ones. We're going to start with sparse transfer learning. So when we click into that, what that's going to take us to is the tutorial that we have for YOLOv5 for transfer learning from it. So I'm just going to drag this over here, and we're going to kind of run through that in a live demo. So we're not going to be able to fully train this model all the way through, unfortunately. It does take a few hours to run to completion on a single GPU, and I'm not going to make you guys wait around for that. But hopefully we can kind of get through and show the full process of what that looks like. So I'm on a cloud instance in AWS that has a V100 on it. What I'm going to do first is just make a sample directory so we can show that we're doing this all from scratch. So make a sample directory, and then let's change into it. Next, what we're going to do is set up a virtual environment. One note is that for this, we do need at least Python 3.7. This is a restriction on Ultralytics. They require at least Python 3.7 to run. So we're just going to use a Python 3.8. And then I'm going to go ahead and activate that. So running in a virtual environment, just again, to keep everything contained. That's generally the flow that we recommend for this. It keeps all the package requirements in the correct state so you can work through these. Next, what we'll do is clone the repo so we can get all this data. So you'll see inside of here, we recommend going through the readme. So that's what we're going through right now. Just going through general setup. So we're going to clone that. What we'll see here, oops. What we'll see here is that we clone that sparsified repo. So we're going to change in the sparsified repo and then change into this integration path here. We're going to go with integrations and then use the Ultralytics YOLOv5. So that's what we're working out of right here. This is where all this code is. What you'll see here is that we have a code base where we can just run a setup command. And this is going to go ahead and check out the Ultralytics codebase with our sparsification software on top of it, and also install all the requirements. So it's going through all the requirements right now. Once you run that setup script, you'll be in good state to begin running these models. Let's go ahead and go back then while that's running. So overview. What we walk through is selecting a pre-sparsified model. So you can see the different choices that we have here for the models that you can transfer from. For this one, just to make it go a little bit faster, we're gonna go ahead and grab the YOLOv5S pruned. So this is a sparse FP32 model. In general, what we'll want to do whenever we're using the prune models, usually we want to use those for systems that have AVX2 instructions. There's some instructions in here on how to detect that. Also AVX512 if VNNI is not available. We always recommend the Prune Quantize generally. If you do have VNNI instructions that's available, this is on the newer Intel CPUs that are available. What we'll go through then is after this completes, we're going to walk through setting up the data. So for this tutorial, we're just going to use VLC to transfer one on. But there is a tutorial that Ultralytics created for training on custom data. And so while it's opening, let me go ahead and kick off the VLC. Oops, sorry, I need to change it to our YOLOv5 directory. And let's kick off the download for VLC. So this is just going to download the VLC dataset, and then we'll start doing a training on that afterwards. But again, Ultralytics has a walkthrough on the dataset format that you need to set up to be able to run with this, and it'll work exactly the same with our tools as well. So you can go through this, and it'll show you how to go about leveraging the Ultralytics packages with our Sparsification buffer on top on your own data sets for your custom dataset. So this is going to go through and download VLC. After that, what we're going to do is start transfer learning the model. So while this is running, we'll download the VLC dataset. I'm going to start running through what we have available. So again, just like before, we had some choices of the model that we wanted to use. What we're going to do is the YOLOv5s prune transfer learning. So we'll grab this command, and that's the command we're going to kick off. And so some notes about transfer learning. As we said, you can use this API here to see if your CPU is didnt compatible. If it is, then Quantize is definitely your best bet if you're concerned about performance. Otherwise, we'd recommend running the pruned models. So we're gonna wait for that to complete, and then we can kick it off. The other note is that for these tutorials, we also push up all of our results onto weights and biases. So this is the results of sparse transfer learning of all these commands up here finishing, and the results that we get on weights and biases. So I can go ahead and open that up. Our weights and biases project, and I'll show that while we're waiting on that data set to complete download, which it looks like it did, and now it's just going through formatting for that. So what we're opening up now is the weights and biases runs that we have. So this is so you can look at how those runs did and compare them to how your runs might do. So this just walks through all the different runs that we did. As long as we can get it loaded. Almost there. Looks like my network's running a little bit slow, but yeah. So you can see all the runs that we ran. We also ran the baseline dense model. So this is just the standard transfer learning run. And then additionally the sparse architectures. So we can see is there are a bunch of different modifiers that we did to control it. But you can see the final results: map, recall, precision, map. In addition, you can actually see some of the results. Let's see, here we go. No. We should have, yeah, here we go. So some test batches for these different runs as well, and you can actually look at different epochs and how that iterated, and also full kind of ROC curves and stuff like that that were created for these. All right, so that is almost done. Go ahead and go back to the tutorial. All right, so again, we're just running through the setup of the data, setup of the VLC dataset, and next we're going to kick off this YOLOv5s prune transfer learning command. So this fully encompasses everything we need to do. What it's telling you to do is use the VLC dataset, use the YOLOv5s model and its config. We're going to pull the weights down from sparse2, which is what we're going to train with, and then run some hyperparameters, and then finally use a recipe. So the recipe also encodes how we transfer learn, and the recipe is important here because we want to keep the sparse architecture there. So we edit the training process so that we can guarantee that that sparse architecture stays in place. So now that we have that, we're going to go ahead and kick off that command, and this is going to start training. So, and if you have weights and biases installed, it'll actually go through and use weights and biases. So if you're going through weights and biases, you can run that. Additionally, all this logs out to TensorBoard as well for local viewing of these results, and also all the information is logged logged out in the command here, as well as to store text files. So this is kickoff. This is going to take some time to run through. We're not going to be able to finish this in here. But the last thing I want to show is once this completes, what we'll do is export the model for inference. And what we'll do is we'll use model/export.py and pass in the path to the sparsified weight, so the checkpoint that's created by this training command. And what we'll see is it creates an Onyx file. And the Onyx file is actually what Deep Sparse uses. You can also use it with Onyx Runtime and a few other systems, including TensorRT and others, to be able to convert these models into compatible formats that different engines can use. So deep sparse uses Onyx, and that's what we'll create once we've run this mod. So that would be the next step after this training run completes. All right. So before we jump into benchmarking, I'm just going to see if we have any questions that are open. It looks like we have one that is asking for a Docker for this tutorial. It's a great question. Currently, we do not. We're actually looking at both getting Dockers up for this, as well as getting this on the collab. So those are future tasks for us that we want to get out soon. But as you know, there's a lot of stuff to do at startups. So so we can run. So you know, it's on the future list to do to make this even easier. And then there's another question on, is it possible to change the recipe? So there are a few different ways that you could change the recipe. One is, for example, so we have a recipe here that goes through and sparsifies those models. Actually, let me pull up a recipe real fast of what those look like. So if you wanted to go through the apply a recipe tutorial that we have inside of here, what you could do is edit one of these recipes to make it more sparse, for example. So I'll pull up the YOLOv5 prune recipe. Let's go to the raw because this is a little bit easier to read whenever we're in the raw mode. These are markdown files which contain instructions for the model, at the bottom, but also they contain a YAML front matter. And the YAML front matter is actually the recipe that we load. So what you'll see up here is we try to make these very legible for people to come in and edit. So if you wanted to, for example, to make this more sparse, what you could do is change the sparsity to create an even more sparse model in case you don't want to recover as much. Okay. And then there was another question that came in about trying out a different activation than Partswitch. Any advice about that? So yeah, so what we'll see is actually for these model configs, for the hard, inside these model configs, sorry, 1 second as this loads. All right, so let's pull up the YOLOv5 So these are the model configs that are actually stored in Ultralytics. And what we did is we added Partswitch in to be able to use here, so that mainly so we could get more performance in the engine. We try and sub in Swish, for example. Swish takes a long time to run. It's usually not very performant for most engines. But for example, you could sub in Raylu here, and Raylu would run faster and be much more generally supported. So what we could do is change the activation function here, but you would likely have to train from scratch, or at least fine tune for quite a bit longer to be able to get that to work. But yeah, so these models are completely coded by this hard switch right here, which is just saying activation equal hard switch. And for example, you could change this over to Raylu or any other torch activation that's supported. Okay. And then there's another question that came in on, do you have different sparsity levels per layer, or is it uniform? So this is actually the hard part about trying to find these recipes so that they recover, and also that we can get performance on them. Uniform sparsity across all layers doesn't work very well for recovery. There are not all layers are created equal. There are smaller layers like 1x1s or 3x3s, smaller channel sizes, larger channel sizes, and so on. And a general rule of thumb is that the more parameters that you have in a convolution, or just in a general neural network, the more parameters in a layer that you have versus the amount of information flowing through it, the more critical it is. So for example, if we have a 1x1 convolution versus a 3x3 convolution with the same number of channels, the 3x3 is going to be much more prunable, so meaning we can set a higher sparsity to it than the 1x1. Additionally, if it's a very wide 1x1, like we get to later on in these networks, then we can prune that to a higher level. So generally what we'll do is we'll set 4 target sparsities and then group the layers across those 4 target sparsities. So we'll have layers that are extremely sensitive, we prune to 60%. Layers that are kind of in the lower end of, the higher end of sensitivity, but not extremely sensitive, we'll set to 75%, for example. Layers that are in the middle in terms of sensitivity are 85%. And then layers that are not sensitive at all, so like the large 3x3s, those are set to 90% sparse. So this is generally what we'll go through whenever we're creating these recipes, is trying to figure out how sensitive each layer is and how much it affects performance, and therefore how we should target sparsity for it. And what you'll see down here is that we have different pruning modifiers. These just tell the code to prune all these layers to whatever our sparsity was.
Hey, Mark, we have somebody raising their hand.
Yeah, go ahead.
Could be a mistake. So Manico, I'm gonna unmute you and allow you to talk. All right. You are permitted.
Oh, hi. Oh, hello. Okay. Yeah, recipe looks great. My concern or maybe just a worry is that the recipe is highly tuned for the training set. So from your experience, how much I worry about distribution drift and other things like that? Thank you.
Yeah, it's a great question. So in general, we've tried running these recipes across a few different data sets. And usually the only thing that we have to edit about them is the number of epochs, the sparsity level. So again, we're creating this general sparse architecture that works really well. These hyperparameters that we're choosing here all generally work across most data sets. It's mainly that we'll just have to shift the number of epochs that we're running, right? So if we have a smaller data set, usually we'll want to run a fewer number of epochs versus a larger one. For example. So usually that's all that we have to change about them. The hard part about the sparsity levels is one, figuring out how to group these layers in terms of sensitivity. That is essentially creating a general sparse architecture that works across most data sets. So that part is very transferable, in addition to how long to prune over and how long to fine tune over. So that ratio is also transferable across data sets. The one thing that isn't really transferable across it is generally the number of epochs that we run for. And that can be edited as needed across the data sets. Again, the one thing that we would really push people to, though, is that if you are using your own data set, to really try out the sparse transfer learning, mainly because that generally transfers much better as you're getting at. Transfers much better across data sets, because this is creating the general sparse architecture that works well across more data sets. And that way you don't have to worry about editing the number of epochs or anything like that. And so, yeah, I think that's, let's see, any rule of thumb for which layers might be at what sensitivity? Yeah, so that is a great question. We actually have a few APIs in there to be able to do that. We're also doing a revamp of those APIs. So generally what we'll do is we'll look at the total magnitude, the average magnitude of each layer. So we take the absolute value and then the average across all the weights across all the layers and group those just by layer. What we'll do then is order those. And that's usually a very, very good metric for which layers are more sensitive than others. For example, a layer that is very sensitive usually has much higher values in it, higher percentage of values versus a layer that is not as sensitive. So this kind of gets into why pruning works, which is that both any kind of gradient descent optimization combined with regularization pushes any unused weights towards zero. So a layer that has more weights further from zero is going to be more sensitive than a layer that does not. So we have a few APIs in the code base to be able to visualize this and see this. And there's going to be actually an entire project that we're kicking off soon that'll wrap that up into a nice, easy to use API, so you can visualize that and also auto create these recipes. So that's something that we're very excited for, and be able to kind of iterate on top of that in terms of our rules of thumb and trying to code those into an Oracle so that everybody can use those and improve on those.
Hey, Mark, we have one question in the chat here. And it says, does deep sparse work better for multi-core processors, or does it provide speed up on single core processors as well? Yeah,
so it's a great question. Multi-core, we definitely specialize more in. Mainly just because obviously as you kind of scale these out in server environments, it's easier to deploy a multi-core than it is on a single core, at least as far as VMs. But you will definitely see performance gains with the sparse and the quantized models on single core as well. The problem is just that as we reduce the cores, we are increasing essentially the amount of compute we have that we have to do, right? Because we're not able to parallelize as much. So the models typically become more compute bound, which also does work out well with sparsity. So I can't say, for sure what the ratio scalings are going to be here for 1 core versus 4 core, for example, but we have definitely tested out all these results across a numerous range of single core processors versus multi-core processors, and all of them see speed up in terms of that. All right, so I'm going to go ahead and jump over to the benchmarking example now. I'm going to go back in here and we'll click on the benchmark button. So what this is going to take us to is an example inside of deep sparse and show us how to run this. So what I'm going to do is the same thing that I did before with the Spark transfer learning, and we're going to create a sample directory to execute on. So we'll do this from scratch. Additionally, we are going to create a virtual environment to run out of as well, just as general kind of good practices of housekeeping, to make sure that our requirements are all contained. All right, and then what we'll do is we'll clone the deep spark repo. We're going to clone that repo so we can get this example that we're looking at inside of Ultralex YOLO, and we can run some commands through that. So we clone that. What we're going to do then is cd into where this example is. So where this all lives inside of example Ultralex YOLO. Right inside of benchmarking, and then the final thing what you'll see up above is that we have to install requirements. We walk through that in the README, but we're just going to install requirements. What this is going to do, and this is install deep sparse, as well as the additional libraries that we need to be able to run this example, this benchmarking, as well as other examples that are contained inside of this folder. So it's going to go through and install, and once it's installed, we're ready to start running some benchmarks. And we should be good in a second, and then we can go to kick that off. And just some background. So I'm running on a C5 12x large instance for this on AWS. This is a 24 core instance. So what we're going to be seeing is 24 core numbers, and we can also scale this down to fewer cores. If we open up the benchmark file, what we'll see inside of here is some command help and just kind of general help for it, as well as general arguments. So we can actually show what the core scaling looks like for the number of cores as was asked before for this. So what I'm going to do is just use that example that we had. I want to keep that one open, so let's click on this one. So keep this open so we can come back to the arguments. So all that I'm doing is running this command right here. So what we're going to do is use, this one right here. We're going to run a YOLOv5 prune quantized benchmark run. We're going to kick that off, and we're going to go ahead and run that. This is going to be for batch size 1, and then we're just telling it to pass it in quantized inputs. It's going to load the data set, automatically download the model, and then we're already done because YOLOv5 runs extremely fast. So this ran at 121 images per second. Additionally, what we can do is change out the tag that we're using. The model stubs are all up here for reference for different runs that you might want to do. And we can do YOLOv5L, for example. So let's go ahead and run the Prune quantized YOLOv5L model. And so it's going to run through. You can see batch size 1, number of cores 24 on one socket. And we came out at 52.2 items per second. That's in comparison to the dense model, which we can run. So let's go ahead and grab the YOLOv5L base, which is our dense model. So we can come in, run the same command, but let's change out that sub for the dense model. 1 second, my backspace doesn't go super quick. Let's go run the dense for comparison. So we got the 52 for YOLOv5L item that was Prune quantized items per second. We're going to download the dense. You can see that the dense takes quite a bit longer to download since it is bigger. And we're going to run that through. We got batch size 1, batch size 24. Oops, sorry, I forgot to get rid of quantized input. We're not quantized anymore. So let's try that again. We're going to kick it off, and this is going to start benchmarking. You can see that we're running. You can already see that we're running quite a bit slower. And we came out at 17. So remember that up above we're at 52.2. Now we're at 17.6. So Again, this is batch size 1. If we were to increase the batch size, we're going to see even more speed up just because of how well it compares there. So dense, we got to 17.6, and then prune quantize, we're able to get to 52.2. So significant speed up there over just batch size 1, and that was for the YOLOv5 result. Additionally, we can try and change this out to number of cores. So as we said, we can actually use the help through the Python benchmarking here, or we can just reference the script here. So if we want to change the number of cores, then we can do dash new cores. And let's do 1. This is going to take quite a bit of time to run, so we might want to try and number of warm-up iterations a little bit. So 2 warm-up iterations of 5, and then we can do a number of iterations at 10, for example, just to try to speed this up a little bit. So this is going to run the dense model on 1 core on this machine. And so we compiled it with Deep Sparse Engine, created the model, and loading the data set. You can see that we're running a little bit slower across batch size, across number of cores at 1. So you see that we got to 1.43 items per second on 1 core. And then let's go ahead and try that with the prune quantize to go back to that question we had earlier. So grab that, let's grab our prune quantize, and then just use those same arguments. We can pass that in, and then we're going to go ahead and compile that one and run that one through for speed up to show the result. So again, we're at 1.43 for dense items per second. And sorry, I forgot to mention that the default here is at 640 by 640 input size. So you can change the input size to also make this run faster. So you got 5.1 as compared to 1.4. So again, a significant speed up for prune quantize over the top of our dense model there. And let's see, we have another question come in from James talking about related questions to CPU scaling. Have you investigated the dependence of the speed up on cache size? Wondering if limiting factor is number/speed of logical cores or something more nuanced. So that is actually a great question. So speed up factor is a very complicated thing to measure. So what we'll see is actually if we run larger batch sizes, what we'll see is this actually scales quite a bit better whenever we run a larger batch size, and that's mainly because we're able to parallelize the compute better. But to your point, for cache sizes and things like that, typically the cache sizes are decently consistent across CPUs, but there is specific code in Deep Sparse to be able to adjust our execution profiles for whatever the cache sizes are, and this is also something that we're actively working on now to even improve the YOLO models even further. So there's a bunch of post-processing at the end that currently we're not leveraging cache as well for. And there's actually a future release that will come out to leverage those caches better to be able to do that. And this is something that we're actually really excited to push out because internally, at least right now, we're seeing at least a 30% speed up across these models for just these cache optimizations, and there's even more that we can do there. So it is something that we're actively looking into, and that the Deep Sparse engine does actually take into account whenever it's trying to figure out how to run this model most performantly. So it's going to take a little bit to run. Probably should have ran it actually. I don't know. I don't know if we're committed too much now to kill this. I think we are, but probably should have ran it at a fewer number of iterations. So just to kind of talk over that, what we do for benchmarking is we're going to run a few warm-ups. This is to stabilize the system, so that we know what our stable system is in whenever we're running. So we'll run a certain number of warm-ups, and then after that, we'll run a certain number of iterations that are actually timed. What you'll see here is that we're running 25 warm-up iterations, and then after that, we're going to run 80 benchmarking iterations. And the 80 are the ones that we're timing and recording the values for, as we saw up here. All right, and let's give that another minute, and hopefully it'll complete soon. But let's see if we had any other questions that were coming in. All right, and then while that's running, some other things that we talk over are kind of the example application, example deployment. So example application, for example, probably should have said that a little bit better, but the example application, we have an annotate.py file Let's wait for GitHub to catch up. We have an annotation example. So what this will do is actually the video that we showed earlier is what this was generated from. So the annotate.py will try and take over your webcam, or you can give it a file and you can actually see the results live on your own machine if you'd like to. Additionally, what we have is a example server. So this will allow you to spin up a server and then be able to send inputs over to it with a client. So we have an example there of what a server deployment would look like. So we ended up at 22.4. This was batch size 32, so a throughput use case. Batch size 32 for the didnt model. And then let's see what the prune quantized model does. Let's grab that, prune quantized, and let's change this over to batch size 32. So again, this just allows us to, the batch size 32 allows, just like with GPUs and other devices, allows us to parallelize the compute better, so we do actually get better performance as batch size scales up. And let's go and kick this one off. This one should not take anywhere near as long as what the dense model did for batch size 32. And let's see, so there we go, running quite a bit faster. And this one I don't have to talk over too much. So it's almost complete, but as I was saying, through the Sparse2 page, the Getting Started page, we have all kinds of examples here that you guys can play around with. Additionally, we have performance comparisons, which link out to a blog, which will show you kind of more detailed comparisons to how this model did, for example, to across GPUs and other CPUs and things like that, throughput and inference performance. And in addition, has a few charts in our blog posts that we had on this to show the true comparisons here. All right, and as we can see, we hit 99.2 versus 22.4, so significant speed up over the top of batch 32. And then we had another question come in from Shakar. So it was any edge device deployment use cases, ASICs, etc. So this is something that's on our roadmap right now, specifically getting ARM support for the deep sparse engine. But additionally, we can leverage these models for deployment on other edge devices and ASICs. This is something that we're actively looking into to create easier pipelines for this, so that we can still get usefulness out of Spark connector running these models and then deploying on specific edge deployments that people may already be using. But the kind of medium to long term is for us to add ARM support for the deep sparse engine and then be able to leverage everything that we're doing here on those kind of new performant ARM chips that are coming out that have vector instructions and others built in. All right, awesome. So that was everything that I wanted to go through, and we can see if any other questions are coming in. But other than that, thank you guys for listening. Let's see. So a question from Harshit. Is YOLOv5 optimized for low latency systems such as medium scale smartphones as well? So this is a great question. This kind of goes back to that scaling chart that we had. So let me go back to the presentation mode. One second. All right. And just drag this over. So that computer's running a little slow. So we have YOLOv5s, you can see down here, and then YOLOv5L. So the main thing that we got out of the compound scaling is ideally something that can be optimized for low latency systems, such as smartphones. So for example, looking at YOLOv5s, we can see that if we scale the input size really low, we can get, obviously we're not going to get as accurate of a model, but what we can get is a very, very performant model as compared to the larger YOLOv5L one. So this is something that we actively make available through our tutorials and things like that. In addition, especially for smartphone deployments, being able to use these pruned and quantized models significantly reduces the download size that we have, because we can compress these much more, and therefore be able to leverage that, faster download, and hopefully not take up as much space on the user's phone to be able to do these. So what we'd recommend is YOLOv5, trying out the prune quantized YOLOv5s, trying to run that in an Onyx compatible engine on a smartphone. Onyx has quite a few APIs because you can still run the quantized model there. And so get that download and then try that out and run it probably at like a 320 by 320 input size, and that could run pretty performantly on for a low latency system on a smartphone. All right. Well, if we don't have any more questions, we can go ahead and just dive into this again. So just kind of once again, thank you guys for joining in. Really, really enjoy having everybody come through and engage with us. A lot of great questions. More than happy to help anybody out. So next steps, please visit our YOLOv5 page to try it out. We're constantly building on our GitHub at Neural Magic through Sparsifying, Deep Spars, Sparsu, all of those repos. And please join our community on Slack and Discourse. So if you guys run into any issues or have any questions, feel free to post those in Slack and Discourse, as well as on our GitHub issue queue. We have our internal customer success person, Jeannie, is very much on top of those and constantly reminding us to make sure that we're responding to all those that come in. So definitely reach out on there and we'll get back to you guys.